Okay, welcome back. This is going to be 5.1. Oh, great. I'll have to hold on. Yeah, right. So 5.1. Oh, great. Let's try this thing. There we go. All right. What are we doing today? Sequences. I love sequences. One of my favorite topics. Try not to get too excited on you, but sequences, and you've all dealt with them on a lot of those like intelligence test or whatever, they'll go like, what is the next number of the sequence? That's kind of what we're dealing with here. All right, so anyways, we have a more technical definition here in mathematics of a sequence. And a sequence is just a function with the domain on a set of integers. Okay, so it's a function defined defined on the integers. So remember, the integers are the counting numbers and the negative counting numbers and the positive, the counting numbers, the negative counting numbers, and zero. Generally, we'll start at 0 or 1. Okay. Right, so the first kind of problems in the book will just have you write out terms of a sequence. So they'll give you the explicit formula, which they sometimes call other things. A book might call it the general formula as well. I guess they're not using this definition, so it's just E sub n equals the floor of n over 2 times 2, and they should tell you where to start. So in this case, it's for all integers n greater than or equal to 0. Okay. All right, so E sub 1, and maybe I should talk about the floor function. So the floor takes any input and just removes the decimal stuff. Okay, so it's the ceiling. You think of the floor as always rounding down to the nearest integer. The ceiling function will always round up. Okay, so 5.201 will be 5, and then the floor of 7.56. You know how you would normally round up. Floor automatically rounds down, so that will be 7. Okay, so E sub starting. Whoops, I got to start at 0. E sub 0 is the floor of 0 over 2 times 0. I'm trying to remember if I'm recording or not. I hope I'm recording. 0 over 2 is 0. The floor of 0 is 0, and then times 2 is 0. Okay, E sub 1 is the floor of 1 over 2 times 2. 1 over 2 is the same as 0.5, right? And then if we round that down, it's 0. So again, it's 0 times 2, so it's 0. E sub 1, or sorry, E sub 2 now. 2 over 2, which is just 1. And the floor of any integer is just, you get the integer right back. Okay. So the floor of 1 is just 1. So we get 2. E sub 3 will be the floor of 3 halves. Okay, so you know what am I doing? How do I get these numbers? I'm treating this E sub n as a function. It's like E of n, right? Instead of x. And wherever I see this n, I'm substituting in this number here. So I would substitute in the n right there. For E sub 1, it's like E of 1, and you're putting 1 in for n. Okay, sorry if I didn't make that clear. Okay, so anyways, E sub 3 is the floor of 3 halves. Let me go back to my other color. Times 2. Floor of 3 halves is the floor of 1.5, which is 1 again. Times 2 is 2. So the first 4 terms of that sequence, 0, 0, 2, 2. Let's look at another one. So this time we want to find the formula for the sequence. There's something that you commonly want to do. You'll look for patterns and then prove the pattern using induction. Okay. We'll get to the induction stuff a little bit later. For now, we just kind of guess. Right. So I need a formula, and this is a common thing that you'll see in working with sequences. You'll have an alternating negative. So we go positive, negative, or vice versa. Okay. And in those cases, you want to write -1 to the n or -1 to the n plus 1. Okay. And then you can use either formula, but you have to be careful which number you're starting at. So for us, we need that first term to be negative. So in this first formula, I'm going to have to let n be greater than or equal to 1. Okay. For the second formula, I'll have to let n be greater than or equal to 0. And it's just, the goal is to have that first term to be negative with these formulas. So if you want the first term positive, then you kind of have to switch them up. Okay, so that's a common thing that you'll come across. Let's see, number 15, we have a more complicated sequence now. 0, -1/2, 2/3, -3/4, 4/5, -5/6, etc. Okay, so we want an nth term formula for this. First off, we could see there's that oscillating -1, right? So we'll have -1 and then, fill in the blank up there. And then there's going to be some sort of fraction. Okay. And you can kind of look at, there's a sequence right there in the numerator. So 0 is the same as 0 over 1, right? So in the numerator, it's going 0, 1, 2, 3, 4, 5, etc. And the denominator is just 1 bigger. So whatever you put in the numerator, you're going to have to make the denominator 1 bigger than that. Okay. Then we have to pick what n value we want to start at. So to get 0 over 1, I'd have to start with n equals 0. So I'm going to have to say for n greater than or equal to 0. And then I need positive, negative, positive, negative. So to make the first guy positive, I'm going to have to put an n right here, because that would be -1 to the 0 is just +1. Okay, -1 to the 1 is -1. -1 squared is +1. So this has a positive, negative, just like we want, and therefore this formula must be correct. Okay, the next thing is summation notation. If you've done Calc 2, you have seen this. So they show it in Calc 1 as well. If not, I'm going to try to explain it to you here. There's plenty of homework in the web assigned for this section. Okay, so what is this thing? It's just a shorthand way of writing out sums that have kind of patterns in their terms. For a long time, they would just literally write everything out, but people got sick of it and they invented this summation notation. Let's look at number 19. Okay, so it's the sum, and of course I hit the button on the pen, even though it's disabled, it still works somehow. It's a sum from k equals 1 to 5 of k plus 1. And how does this work? What are the identifying pieces? So this is just some Greek symbol, sigma, capital sigma. What else? K is called the index. K equals 1. 1 is the lower limit. That's your starting place. 5 is the upper limit. Okay. So to write out this sum, what you're going to do is plug in 1, and then plus, plug in 2, and then plus, plug in 3, 4, and you're plugging these numbers into this formula here. Okay, and then you go all the way up to the upper limit, which is 5. Okay, so plug in 1, you get 1 plus 1, and then plus, plug in 2, you get 2 plus 1, and then plus, plug in 3, 3 plus 1 plus, etc. Right? And sometimes it's not a bad idea to kind of, if you have a lot going on in your life, write out which ones these are, right? So this is k3, k is 4, k is 5. Sometimes that helps, sometimes not. But anyways, the ultimate goal, we just add them all up. So there's 1, 2, 3, 4, 5 of those, plus 3, 6, 10, 15, which is 20. Okay, so it's, hopefully it's not too bad. Let's look at number 27. This is the sum from n equals 1 to 10 of 1 over n minus 1 over n plus 1. Okay, so I have 1 over 1 minus 1 all over, so this is for n equals 1. 1 over 1 minus 1 over 2. And I'll kind of put them in parentheses just to make my life a little easier. N equals 2, I put 2 in for n, right? So 1 over 2 plus 1 is 3. And then n equals 3. 1 over 3 minus 1 over 4. Okay. And then plus, for n equals 4. 1 over 4 minus 1 over 5. Okay, you sort of getting the pattern down. 5, it's 1 over 5 minus 1 over 6. Okay. And sometimes it gets annoying having to write everything out. So you just put a dot, 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 and then plus, let's put in the last couple, right? So n equals 9, maybe. Take a look at that. So the one before 10 is n equals 9. That'll be 1 over 10 minus 1 over, 1 over 9 minus 1 over 10. And then the last guy, n is 10. I have 1 over 10 minus 1 over 11. Okay. This is a special kind of series. It's called telescoping, and you see it in Calc 2. It's called telescoping because once you expand it, you kind of see that it can be collapsed, right? The spiel is these negative 1/2 plus 1/2 is 0, negative 1/3 plus 1/3 is 0. That will cancel with that. That will cancel that. This will cancel with the guy right in front of it. The guy right behind it will cancel with this guy. This guy will cancel with this guy. And what you're left with is just, in this case, and it doesn't always happen this way, but in this case it did, 1 minus 1 over 11, which is 11 over 11 minus 1 over 11, which is 10 over 11. Okay, so that's a neat one. There's some weird ones, like what do I do when the limits are the same and stuff like that. For example, number 24, j equals 0 to 0. And we have j plus 1 times 2 to the j. Okay, well, all you have to do is plug in j equals 0. So there's just one term, and this is kind of silly to even write. So when j is 0, I have 0 plus 1 times 2 to the 0 equals 1. 0 plus 1 is 1 times 2 to the 0 is 1. 1 times 1 is 1. Okay. Sometimes you can have negative limits. Reversed limits, usually it depends on where you're working. Sometimes I'll just define those to be 0. So if you're going from like 5 to negative 100, 5 in the lower limit and negative 100 in the upper limit, sometimes just define that to be 0, but in other contexts, I'm not sure. I think they might talk about it in Knuth's book on concrete mathematics. It's probably somewhere in there for computer people. But anyways, what's next? Expanding these things more and more. So let's look at one more of these, I guess, number 30, just to make sure we're all on board. The sum. Oh, this one's a little different because the upper index is a variable. So how would I expand that? Okay. So in general, what you want to do is just list the first couple terms and then plus dot 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 plus list the last couple terms like we did back here in this example, right? So you list the first couple terms and then the last couple terms with a dot 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 in the middle. Okay, so let's do that. And so j equals 1 is 1 times 1 plus 1. And you don't have to write the j equals 1 underneath, but I do. J equals 2 is this. And then you just keep going until you get sick of it, basically. 3 times 3 plus 1. So j equals 3. And then plus dot 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 plus. And then you can list the last couple terms. So the very last term will be the nth term. And then the term before it, so j equals n is the last one. To get to the term before it, what do? Well, up above, to go from n equals 10 to n equals 9, what do I do? 10, you just subtract 1 to get the 9. So down here, if you have n, you just subtract 1 and you get n minus 1. And then the one before that, if you want it, n minus 2. And then you're plugging those into you're plugging this n minus 2 into this formula up here. So you would have n minus 2 times n minus 2 plus 1. And you would want to simplify that eventually. Here would be n minus 1 times n minus 1 plus 1. And then finally plus n, so I'm plugging in n this time, times n plus 1. Okay, so hopefully that clears that issue up. Sometimes in induction we need to be able to do this following thing, and basically you're evaluating the sum for the indicated value, but the sum isn't given in summation notation, it's just written out. Okay, so 33 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus dot 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 plus 1 over n squared. Okay, so the weird thing here is that we have basically too much, more than what we need. If we wanted to write out the sum for n equals 3, we would write out this part of it. Okay, but we're asking for something less than that. We just want n equals 1, and what is that? Well, that turns out just to be this guy here. Okay, if you're not 100% on that, you could rewrite it in summation notation and then kind of clear it up in that regard. So what is this as a sum? In summation notation, I'm going from I equals something to something. The formula, I think, is 1 all over I squared. So I'll start at 1 and then go to n, and that will work, right? So in particular, they're asking for n equals 1. So if you plug n equals 1 into this summation, wherever you see n, you're going to put a 1. And we just have a sum from 1 to 1, which is just one term. That's what we were working with above in problem 24, right? So all you get is 1 over 1 squared, which is just 1. In other words, it's just this first term here. Okay. Seems a bit weird. Let's look at one more of those. Here's 34. We have 1 times 1 factorial plus 2 times 2 factorial plus dot 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 plus m times m factorial, and we want to evaluate this thing for m equals 2. So I think what we're after here then is just these first two terms, right? But again, if you're not sure, and sometimes these can get kind of really weird, you can do a sum thing. So I equals, I guess we'll go from 1 to m of I times I factorial. And in particular, we want m equals 2, so you can write the sum I equals 1 to 2 of I times I factorial, which will be plug in 1 and then plug in 2. And it is what we thought, right? It is just that exact same thing. Okie dokie. So that's important for induction, and we'll get to induction later in this chapter. This next problem is kind of important. I came across it a lot in differential equations, maybe not necessarily like intro to differential, but later classes. We have this thing here. We want to separate off the final term. Okay, so how do I do that? You can kind of take the upper limit and just subtract 1 from it. Okay, so you'd have m plus 1 minus 1 k squared, and then plus the thing that you kind of subtracted off. So the last term in this sum would be plugging m plus 1 in for k, right? So the last term here would be m plus 1 squared, and that would do it, right? You want to go back and then clean up the upper limit, so it's a sum from k equals 1 to m of k squared plus this m plus 1 squared. And again, if you don't believe me, you can go through the rigmarole of expanding the thing. So this thing is also equal to 1 plus 2 squared plus 3 squared plus dot 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 plus k equals k, the last one is m plus 1, so the one before it must be m. So plugging in m, you get m squared plus m plus 1 squared. And you see that m plus 1 squared is that last term you separated off. And then all of this rigmarole is the sum from k equals 1 to m of k squared. Okay, which is this rigmarole. Okay. So separating off final terms is important in certain applications. You also want to be able to rewrite these things as single terms, so they'll give you sort of the separated version, and then you have to rewrite it. So you have the sum here from m equals 0 to n of m plus 1 times 2 to the m plus n plus 2 times 2 to the n plus 1. Okay, so we could rewrite that as a sum from m equals 0 to n plus 1 of m plus 1 times 2 to the m. And you can kind of see, if you were to substitute in n plus 1, you're going to be getting this term here. In particular, n plus 1, it will be your n plus 2. So you would have n plus 1 plus 1, and then you would have 2 to the m, which is then n plus 1, and that would be this last term. Okay, so you get a little practice doing that. Another thing that you sometimes have to do in applications is change the limits, or do a transformation of limits, transform the variables in the limits in particular. The book gives you the formula they want you to use, but in general you have to kind of do that on your own, be creative for whatever purposes you are doing. 57, we want to transform the sum I equals 1 to n minus 1 of I all over n minus I squared. Okay, of course, now the button doesn't work. Whenever you want it to work, it doesn't. Rule of thumb. N minus 1. Okay. So what I'm going to do is produce a formula for I. So right now I have j equals I minus 1, but I can rewrite I as equaling j plus 1 just by solving, right? So you add 1 to both sides and you get this new formula. Okay. So to pull off this transformation, one thing to note on the limits is this limit is in terms of I. Okay. Even the upper limit. It means it's going from I equals 1 to I equals n minus 1. And now I want to go from j equals something to j equals something. So what you do is just input these I values into the j formula. Okay, so for I equals 1, I'm taking that 1 and I'm plugging it in to the j formula right there. So j must be, when I is 1, j must be 1 minus 1, which is 0. Okay. Okay. Then for the upper limit, my end answer should be in the upper limit j equals something. Okay. So again, I use the formula. J, when I is n minus 1, j must be n minus 1 minus 1 again. Okay. So n minus 2, in other words. So j will equal n minus 2. We don't write j equals, though. We just write the n minus 2 part. But I mean, literally, in the background noise, there is kind of a j equals in the upper limit. On the inside of the summation, then, I'm replacing all of the I business. Okay, so let me, all of this, wherever I see it, with my formula for I. So I replace the i's with the j plus 1's. So I'll have j plus 1 all over n minus j plus 1, and all that was squared, I think. Okay, and that would be it. And sometimes you have to simplify a little bit, but that's the idea. Okay, so let's try another one. This is 56, and I have the sum from I equals 3 to n of I all over I plus n minus 1. Okay, so this same kind of game. I'm given a formula for j, and I want to now produce a formula for I. So I just add 1 to both sides. And then over here, I'm going from j equals, so when I is 3, j will equal 3 minus 1, which will be 2. And then when I is n, j will equal n minus 1. Okay, so again, it's just substituting in the limits in the original expression into the formula for j. So I'm just substituting these values into that formula. Okay, and then on the inside and the guts here of the summation, I'm just replacing i's with this I formula here. Okay, so let's go ahead and do that. And what do we have? We have j plus 1 all over j plus 1 plus n minus 1. And clearly you would just want to write that as j plus n, but for the sake of time, let's go ahead and move forward. Okay, the next thing you may not have seen, unless you're a hardcore math geek. You'll see it if you take number theory. You may have already seen it if you saw Wallace's formula in Calc 2. Some books will cover that. I don't think I cover that in my classes. Okay. But it's basically just the same thing as summation notation. Instead of adding everything, guess what? You're multiplying everything. Okay, it'll work the same way. Go from 0 to 4 and multiply every term. So when j is 0, you get negative on the 0, and then instead of adding, put multiply. Okay, so then you have negative 1 to the 1, and then negative 1 squared, and then negative 1 cubed, and then negative 1 to the 4th, etc. Right? So this would be 1 times negative 1 times 1 times negative 1 times 1. Or you just add the exponents 7, 8, 9, 10, so that would be an even number, so therefore it's positive. Okay. You can do all the same rigmarole with the product notation. Let I equal k plus 1. So we want to transform the given product using that formula. So right now it's k in terms of k. So we have k all over k squared plus 4. Okay, so I'm going to rewrite my formula in terms of k. So I subtract 1 from both sides, and you get k equals I minus 1. Okay, so in my new product, I'll be going from I equals something to I equals something, and I'm replacing the k in the formula with I minus 1. All right. And then, sure, what do we have to do then? You're placing these numbers for k into the formula for I. So I will go from 2 to n plus 1. Okay. We saw a little bit with factorials way back where. I didn't really talk about them. 34, problem 34, there's some factorial stuff. But we didn't get into the gritty details. We want to do that now. factorials, and n choose r notation, which is used in combinatorics. We have a whole chapter dedicated to permutations and combinations and that kind of stuff later on. Anyways, for now, first a factorial. If you've never seen that before, something like 7 factorial is equal to just 7 times 6 times 5 times 4, 3 times 2 times 1. 5 factorial, 5 times 4 times 3 times 2 times 1. Within every factorial is another factorial, right? So 5 factorial is 5 times 4 factorial. Likewise, then there's another factorial in there. That's just 5 times 4 times 3 factorial. Okay. Some weird ones. What is 1 factorial? Well, that's just 1. What is 0 factorial? Well, that's just 1 as well. If you're worried about why that's true, you can look on number files. They do a whole spiel on that. If you look up factorials and number files on YouTube, got nothing else to do with your day, you can go there. There's other kinds of factorials. There's falling factorials that you'll see in the Knuth book on concrete mathematics. There's the sort of the gamma notation for factorials, I think, which will put factorials in terms of integrals, I think. I don't remember, but anyways, for us, there's kind of like this brute force and then recursive definition. So I'll just say brute definition, which is kind of what we were just doing above, but we want to put everything in general terms. Okay, so the brute definition, n factorial. Brute, I mean just listing everything out. So n factorial is n times, guess what? 1 less than n. So n minus 1, and then times 1 less than n minus 1, it should be n minus 1 minus 1, which is n minus 2. And then it just keeps going into 3 times 2 times 1. Always ends in 3 times 2 times 1, unless your number is less than 3. For example, 1 factorial does not end in 3 times 2 times 1. Then the recursive definition, which I like much more than the brute definition, but for some reason it kind of goes over people's heads, is just that n factorial can be rewritten as n times n minus 1 factorial. Okay? And then on top of that, n times n minus 1 factorial would be n times n minus 1 times n minus 2 factorial, and so on. Okay, so let's take a look at some of the exercises, and there'll be a ton of them in the WebAssign for your enjoyment. 6 factorial over 8 factorial. My hand hurts, so I'm not going to write all this out. I use the recursive definition, right? So 8 factorial is really 8 times 7 factorial. 7 factorial is really 7 times 6 factorial. Okay? And as soon as I see a cancellation, 6 factorial over 6 factorial is 1 over 1. I can remove those, and I'm just left with 1 over 8 times 7, 5, 6, 7, 8, right? 1 over 56. What else? 67. So those aren't so bad, but 67, now we get into more general expressions like you would see in Calc 2 when you're dealing with like Maclaurin polynomials and stuff like that. Again, I'm going to use recursive definition for a cancellation. So n factorial is the same as n times n minus 1 factorial. N minus 1 factorial is the same as n minus 1 times n minus 2 factorial. And now I have a cancellation that'll happen, right? So these will cancel, and you'll be left with n times n minus 1. A little bit harder now, number 70. You might see something like this maybe in like the binomial theorem. When you're working with expanding certain products. How do I do this? Okay, so n factorial is greater than n minus something factorial, right? So I'm going to use a recursive definition on the numerator until I get a factor that equals this denominator here. Okay, so I'll go n times, I don't want to write that in red. It's not going to let me do anything else, apparently. N times n minus 1 times n minus 2, dot, dot, dot. And I need to get all the way down to n minus k plus 1. Okay. In particular, I need the one before it, because then I'll know how far the cancellation goes. So I need to go all the way down to n minus k plus 1 factorial. Okay. And then I'll have my nice cancellation. Okay, so I just need the one above it. So to get to the one above it, what do you need to do? You need to add in 1. So before, when you do factorial and you're going down, you subtract 1. In this direction, you need to add in 1. Okay, so you're going to have n minus k plus 1 plus 1. In other words, n minus k plus 2. All right, so then you can do your cancellations and everybody's happy. Be n times n minus 1 times n minus 2, dot, 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 all the way down to n minus k plus 2. Okay. All right, the next topic then is the n choose r notation. N choose r, or n choose r. Okay, they also write n choose r. The number of ways you can pick r distinct elements from a set of n without regards to order, something like that. We'll be looking at that later on in upcoming chapters. For now, we just kind of work with it as a type of function, a multivariable function, and in particular the definition for all n comma r in the integers such that 0 is less than or equal to r is less than or equal to n, and choose r is equal to n factorial all over r factorial times n minus r factorial. Okay. Okie dokie. So let's take a look. 71. We have 5 choose 3. Okay, so that'll be 5 factorial all over 3 factorial times 5 minus 3 factorial. And then you simplify using order of operations. Upstairs we have, and I probably want to eventually use a recursive definition on this, 5 times 4 times 3 factorial all over 3 factorial times 2 factorial. 5 minus 3 is 2, so that'll be 2 factorial. These will cancel. 2 factorial is the same as 2. 2 goes in the 4 2 times. So we'll have 5 times 2, which is 10. 74. What the heck is 5 choose 5? Turns out to be 1, right? So 5 factorial all over 5 factorial times 5 minus 5 factorial. The 5 factorials cancel, so I have 1 all over 5 minus 5 is 0 factorial. Of course, 0 factorial is 1. Just weird peculiarity. 0 factorial, 1 factorial, 2 factorial, 3 factorial is the same as 1, 1, 2, 6. Okay. 4 factorial is 24. Okay. So sometimes in Calc 2 people get confused because you'll write it as 1, 1, 2, 6, and really you're talking about factorials, but they're kind of the same thing. Okay, maybe that's not an issue, I don't know. Anyways, going to more general problems with variables. So for example, n plus 1 choose n minus 1. I want to simplify this. Sometimes you'll do that to identify combinatorial identities. There used to be books. You go to the library, there's just literally books of combinatorial identities. Like there's books of integrals back in the day before they had calculators that could do integrals, which probably none of you remember, but I do. Anyways, this thing is n plus 1 factorial all over n minus 1 factorial times n plus 1 minus n minus 1 factorial. Okay, so this is n plus 1. factorial all over n minus 1 factorial times n minus n is 0, and then 1 plus 1, so just 2. And then I can simplify the numerator and the denominator with the recursive definition. So n plus 1 times n minus 1 factorial. And there'll be a nice cancellation there. 2. So the n minus 1 factorials cancel. You get n plus 1 times n all over 2, which I believe is also the sum from I equals 1 to n of n. Or sorry, I. Okay, it's also the same thing. So there has to be some weird identity going on there. Okay. All right. So what else? Doing proofs with these. So later on, like I said, I maybe be proving combinatorial identities, which sometimes will make life easier if that's all you do all day long. They have people that do combinatorics like at AT&T. At least they used to hire them. I think it's mostly just computer science now. But prove for all n are in the non-negative integers. So that would be all the positive counting numbers plus 0 with r plus 1 less than or equal to n. Show that n choose r plus 1 is equal to n minus r divided by r plus 1 times n choose r. Okay, so it's more like a trig proof back in the day than our direct proof, but we'll set it up like a direct proof. We'll start with our supposition. So suppose n and r are our payback non-negative integers such that r plus 1 is less than or equal to n. Okay, we kind of want to show, and this is WTS is want to show. In this part, what I'm going to do is kind of do some of the work, get it out of the way, right? So it's kind of a clever way of making my proof kind of formal, but at the same time doing some of the legwork. So what I want to show is that this thing is equal to n minus r all over r plus 1, and then I want to think about my goal, right? So what is n choose r? That's n factorial all over r factorial times n minus r factorial. Okay, so just simplifying my proof a little bit and thinking about my ultimate goal. You know, if I could show this, then I will have shown it. If I could show that this guy equals that, then I'm kind of done. Okay. So I want to show that. I'll start on the left-hand side. So note by definition, n choose r plus 1 is equal to n factorial all over r plus 1 factorial times n minus r plus 1, right, which will be n minus r minus 1 factorial. Okay, so I'm trying to connect it to the stuff in yellow up there. And the stuff in yellow is very, very similar. So I'll have the n factorial part. That's kind of good to go. The r plus 1 factorial is a lot like the r plus 1, right? All I have to do is peel off one factor using the recursive definition, and then I'll have that. So it'll be r plus 1 times r factorial. That's what I rewrote r plus 1 factorial as. And that's a good thing because now I'll have the r plus 1 here and then the r factorial here. Okay, so I'm kind of just, maybe in green, these are the things I have, right? I have this, I have this, I have this. Okay, I need an r minus n in the numerator. Okay, so you pull a trick. Just multiply top and bottom by n minus r. Okay, and now I also have this thing. So the only thing I need is the n minus r factorial. Okay, so what do I have left from the previous step? I have n minus r minus 1 factorial. Okay, well, here you can kind of note that these two terms are just the reverse of the recursive definition and give me n minus r factorial. In particular, this first term is n minus r, and then if you subtract 1, n minus r minus 1 would be the next term in that factorial sort of progression. So that turns out to be the n minus r factorial that we were after in the yellow box. Okay, so that will equal then n factorial all over times n minus r all over r plus 1 times r factorial times n minus r factorial. And then we could rewrite it using our associative, or rather commutative properties of multiplication. We want to put the n minus r first, all over r plus 1. That's this chunk. And then times the n factorial all over r factorial times n minus r, which is exactly what we have in the yellow box. And so we're done. That's what we wanted to show. Okay, which is what we wanted to show. Okay, and then we're done. All right, so good stuff. The last part in this section is working with algorithms, in particular converting decimal to binary, which every good computer person should know how to do. What is that? What did I say? Decimal into binary. I'm not going to be worrying about like converting fractions in the binary or anything like that. You can always do that as well. You can have like 1, 0, 1, 1, 0.1, 0, 1, 1, I think, stuff like that. If you're interested in that, let's look it up on the internet. I don't do that. But anyways, going from decimal to binary, in the first couple of problems, they'll want you to do this just by hand, by doing it by long division. For example, number 81, they want you to convert 90 into a binary number and do it by long division. So how does that work? Okay, so you go 90, and you're going to just keep dividing by 2. So 90 divided by 2 leaves me with a remainder, right? So over here, long division, 90 divided by 2, 4, 8, carry down a 1, 0, 5, 10, 0. So the remainder is 0. And then I'm going to take this next number, this 45 up here, okay? And that'll be the next number I work with. So 45 divided by 2, okay? And then I worry about the remainder there. So 2 into 45 goes 2 times 4, 0, bring down the 5. That goes another 2 times. That'll be 4. So a remainder of 1. And then my new number will be 22 divided by 2. So it's an even number, it's remainder 0. Odd number, remainder 1. So that'll be 0. And then 11. 22 divided by 2 is 11. And I have to divide that by 2. That would be odd, so remainder 1. And then 5 divided by 2, that's odd again, remainder 1. That'll be 2 divided by 2, that's even, remainder 0. And you always end with 1 divided by 2, which will be remainder 1, right? Okay, so your binary number is sitting right here. And you read it in reverse, so it would be 1, 0, 1, 1, 0, 1, 0. The algorithm for working with this is basically just the same thing, but in a mechanical type form. So in particular, this number here is from doing mod 90 mod 2. And then on the other side, this guy right here is from doing div. So this is 45 div 2. Okay. And that's pretty much it. So you're replacing, you'll call this 90q, and you'll replace q with the 90 div 2. So sorry, so this is 90 div 2. Okay, and then this guy will be, this next number in your binary expansion will be the new q mod 2, and then this number will be q div 2, and then this number is the new q mod 2, and then this number is the new q div 2, etc. Okay, so we just need to put that into code and go with it, right? So this one would be then 11 mod 2, etc. Okay, so let's try. Well, I guess the code's given in the book. The algorithm is 5.1.1. So we don't even have to write it. So you could try putting this in Python. No extra credit this time, though. Sorry. Decimal to binary. Still good practice to fool around with your computing code, but you probably have bigger projects to worry about if you're doing computer stuff. Input is going to be some n value. In our case, above it was 90, and then the algorithm body. You'll define q to be n and start I at 0, and then you have a while statement. While I is 0 or q is not 0, then you execute the code. So while that's true, you will build an array which will contain our binary number. So that will be the q div, or sorry, q mod 2. And then q we're going to replace with q div 2. And then we increment I and keep repeating until q goes to 0. And then the output is that array, which is just in a list of numbers, right? So it'd be R0, R1, R of 2, all the way up to R of I minus 1. Okay. Okay, so let's see if we can do a trace chart for this. And clearly in the book, or in their homework, it's a lot easier because it's just fill in the blanks. I'll introduce the trace chart. I'm not going to go through the whole thing, but it's kind of difficult because I wish I could put it on the side. I should have made my algorithm smaller so we could read it. But anyways, I'll let T be for iterations, and then the N is the initial input, and then Q, we need an I, and then we'll start listing our array elements below this R sub I. Okay. I don't know how far I'll go with this. But start at not in the loop at all. And N is given by the user to be 90. Q is initially defined to be 90. I is set to 0. And we don't have any R sub i's yet. Okay, so then we start going through the while statement. Here, I is 0, so that OR statement will be true. And we can then go ahead and get our first R sub 1, or R of 0, sorry. So in the loop here, R of 0 will be Q mod 2, which is 0. Then Q will be redefined to be Q div 2, which is 45, and then I is incremented. Okay. q is not 0, so the or statement's true, so we go still into the while. We're going to now have an R1 being defined as q mod 2, which will be 1. And then we replace q with div. Q div 2 will be 22, and then increment your I. Okay, q is still not 0, so we go R, instantiate this R2 position in the list. So where are we? R2 will be 22 mod 2, which is 0. Q replace 22 div 2, 11, and then increment I. Q is still not 0, so we can instantiate R3 as 1, and then Q div 2 is 5, and then I goes to 4. Need a little more room there. Guess I'm gonna pull it off. So Q is still not 0, so I can instantiate another R. So R4 will be 1, Q5 div 2 will be 2, I goes to 5. Q is still not 0, so instantiate R5. So Q mod 2 is 0. 2 div 2 is 1. Go to 6. Q still not 0. We need one more, right? So 7. So instantiate another position, R6 in the array. And 1 mod 2 is 1. 1 div 2 is 0. Increment 7. Now Q is 0 and I is not 0. So both of those statements in the while condition are false. I is not 0, and Q is equal to 0. So we end the while loop, and the output is this array here, this list, which is the binary number 490. Okay, so 1 0 1 1 0 1 0. Okie dokie. I think that'll do it. We'll see you next time.